So this video is the last part of the trig review. So first of all, we think of wherever the side where an angle starts as being the initial side of an angle. The vertex is the common endpoint of an angle, but we think of the where the angle starts as being the initial side. And we think of where the angle ends as being the terminal side. Now, in the xy plane, we think of an angle being considered to be in standard position if the initial side of the angle is on the positive x-axis, and then the terminal side of the angle is somewhere else in the xy plane. Or it can also be on the positive x-axis. That would just end up being an angle of 0 or 2 pi. So we consider whenever the angle rotates in a counterclockwise direction to be creating a positive angle. So like all the angles on the unit circle are positive angles. We think of them as starting on the positive x-axis and then rotating in the counterclockwise direction. But angles that rotate in the clockwise direction we actually think of as being negative angles. It can be really helpful to be able to determine what quadrant an angle terminates in, but also just have kind of the awareness of where different angles terminate. So like 400 degrees, that's more than one full rotation. So if we were to draw an angle that measures 400 degrees in the xy plane, we know that it's a positive angle. It starts on the positive x-axis, and then it must rotate all the way around in the counterclockwise direction, and then it will go 40 degrees back into quadrant 1 to terminate in quadrant 1. Negative 150 degrees, well, it's a negative angle, so it would be rotating in the clockwise direction. It would be starting on the positive x-axis and then rotating in the counterclockwise direction. The clockwise direction. So it would end up terminating about there. Right, because if it went all the way to the negative x-axis, that would be negative 180 degrees, and it's so it would end up terminating in quadrant 3. Seven pi over 12, positive angle, so rotating in the counterclockwise direction. Starts on the positive x-axis and then rotates in the counterclockwise direction. Now, pi over 2 would be equal to 6 pi over 12. And pi would be equal to 12 pi over 12. So that means that 7 pi over 12 must terminate in quadrant 2. And then negative pi over 2, it's a negative angle, so it must be rotating in the clockwise direction. And it's not actually terminating in a quadrant. So this is a little bit of a trick question. It would end up terminating on the negative y-axis. And would end up terminating in the same position as the positive angle 3 pi over 2. So that kind of leads us into coterminal angles, right? Because negative pi over 2 would terminate in the same position as 3 pi over 2. That's the idea behind coterminal angles. angles that terminate in the same position. So they share a terminal side. And every angle has infinitely many coterminal angles, infinitely many angles that terminate in that same position. And you can find coterminal angles by adding or subtracting multiples of 360 degrees or multiples of 2 pi. So like for negative pi over 2, if we were to add 2 pi to negative pi over 2, that would put us at 3 pi over 2. They are coterminal angles. It can be helpful for us to find the smallest non-negative coterminal angle of an angle, because if that smallest non-negative coterminal angle is an angle from the unit circle, then we will be able to evaluate any of the 6 trig functions for that angle. So if you have an angle that's outside of 0 to 2 pi or 0 degrees to 360 degrees, and you're trying to evaluate sine, cosine, tangent, or any of the reciprocal trig functions for that angle, you can try to find the angle's coterminal angle that is between 0 and 360 degrees or 0 and 2 pi. And if that angle is from the unit circle, then you can evaluate the trig function for the original angle, because you'll have the same ratios of the trig functions. So let's first start with practicing finding the smallest possible positive coterminal angle given these 3 angles. So for 900 degrees, if we were to subtract 360 degrees, we would still be more than 1 rotation. So let's think about subtracting 2 rotations, or subtracting 720 degrees. That puts us at 180 degrees. So 900 degrees and 180 degrees are coterminal angles. Then for negative 430 degrees, well, again, if we were to add, that's more than 1 rotation in the clockwise direction. If we were to add 360, we would still be in the negative. So let's go ahead and add 720 degrees, and that puts us at 290 degrees. And then if we thought about adding 2 pi to negative 13 pi over 6, that would just be adding 12 pi over 6, which we would still be in the negative. So we're going to think about adding 24 pi over 6, which is like adding 4 pi. And that puts us at 11 pi over 6. So 11 pi over 6 is coterminal with negative 13 pi over 6. So to evaluate the trig functions for these angles that are not between 0 and 360 degrees or 0 and 2 pi, we're going to think about finding the positive coterminal angle that is on those intervals. So for sine of negative 480 degrees, well, we can think about adding (720 degrees) and that gives us sine of 240 degrees. 240 degrees is on the unit circle. That would be negative root 3 over 2. Okay, so for cosine of 23 pi over 6, well, 12 pi over 6 would be 2 pi. So we can think about subtracting 12 pi over 6. And we would get 11 pi over 6. Which would be positive root 3 over 2. Okay, and then for secant of 900 degrees, well, we could find the coterminal angle first. So that would be equal to secant of 180 degrees. Secant is the reciprocal of cosine. So this would be 1 over cosine of 180 degrees. Cosine of 180 degrees is -1, and its reciprocal would just be -1. Cosecant of -10 pi over 3. Well, if we added 6 pi over 3, which would be adding 2 pi, we would still be in the negative. So we're going to think about adding 12 pi over 3. Cosecant is the reciprocal of sine. Sine of 2 pi over 3 would be √3 over 2, so that reciprocal would be 2 over √3, where then if we rationalize the denominator by multiplying by √3 over √3, that would be 2 √3 over 3. So next we're going to talk about the graphs of the parent functions for sine and cosine. So all of the trig functions are what we call periodic functions. Graphically, that means that over the length of a certain interval, the pattern of the graph ends up repeating itself over and over and over again. So that's what this means for f of x plus p equals to f of x, is that for all x in the domain of f, is that if you think about there being the length of a certain interval and taking that interval, the length of that interval, and adding it to every x value in the interval, the pattern, all of the outputs of the function will end up repeating in the exact same order. And that's how you end up with a repeating pattern in the graph, is that all the function values repeat in the exact same order. So like I said, the trig functions are all periodic. And surprise, surprise, 2 pi is actually the fundamental period for sine and cosine, right? We were just talking about coterminal angles, how every angle has infinitely many coterminal angles that just differ by multiples of 2 pi. So for sine and cosine, their fundamental periods are 2 pi. For tangent and cotangent, they're pi. Like all the values of tangent and cotangent will repeat again every pi units. We use radian measure whenever, for the angles, for the inputs of the trig functions, whenever we're thinking about their graphs, because remember the xy plane is the intersection of two real number lines, and radians are real numbers. So we want to be in radian measure, especially when we're graphing on our calculators. So I'm going to fill in this table of values for sine, just thinking about unit circle. Sine of 0 is 0. Sine of pi over 4 is positive √2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 would be √2 over 2. Sine of pi is 0. Sine of 5 pi over 4 is negative √2 over 2. Sine of 3 pi over 2 is -1. Sine of 7 pi over 4 is negative √2 over 2. And then sine of 2 pi is 0. So plotting those points, I'm first going to finish labeling the y-axis here. Halfway between 0 and pi over 2 would be pi over 4. So this would be 5 pi over 4, 7 pi over 4, or sorry, I skipped 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay, and then root 2 over 2 is approximately 0.707. So just under there, sketching from 0 to 2 pi, the graph of sine. There should be no sharp corners. Sine is differentiable everywhere, right? You know the derivative of sine is cosine, and cosine has a domain of all real numbers. So that's one period of sine. Sine passes through the origin. Its parent function does, at least. It's non-shifted function does. Okay, and then because we know the pattern of sine, we can just extend the graph in either direction if needed without having to really think too much. And I'm going to draw arrows to indicate the graph would continue on. So domain of sine is all real numbers. The range is -1 to 1. You can see that the graph bounces back and forth. It oscillates between -1 and 1. Sine is an odd function, which means that the graph is symmetric about the origin. So what that means is that when we apply a horizontal reflection, it looks the same as a vertical reflection. So looking at the graph, a horizontal reflection would look the same as a vertical reflection. So sine of -x is equal to negative sine of x. And that can be helpful to us when we're trying to evaluate sine for negative angles, because we can just think about pulling that negative out. Like if you wanted to evaluate sine of negative pi over 4, that's equal, instead of finding the coterminal angle to negative pi over 4, which you can do, you can pull out the negative and go sine of pi over 4 is root 2 over 2. Oh, that's equal to negative root 2 over 2. So it can be a shortcut for evaluating the trig functions as well. And then we already talked about how sine's fundamental period is 2 pi. Cosine, filling in the table, cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 2 is 0. Cosine of 3 pi over 4 is negative root 2 over 2. Cosine of pi is -1. Cosine of 5 pi over 4 is negative root 2 over 2. Cosine of 3 pi over 2 is 0. 7 pi over 4 is root 2 over 2. And then cosine of 2 pi would be back to positive 1. So again, labeling my y-axis. Okay. Again, root 2 over 2 is approximately 707. So we're starting up at 1 and then coming down, passing through the x-axis, go to the lowest point down at -1, and then we come back up. Okay, so just like sine, we can extend the graph without having to think too much. Just extending the same pattern, the points. Drawing arrows to indicate the graph goes in both directions, extends in both directions forever. The domain of cosine, like sine, is all real numbers, and the range is also -1 to 1. Cosine is an even function because a horizontal reflection does nothing to the graph of the original function. Right? If we apply a horizontal reflection, the graph looks the same. This can also be helpful for evaluating cosine for negative angles, like cosine of negative pi over 4 is just going to be equal to cosine of pi over 4, which is root 2 over 2. So it can also be another shortcut instead of finding coterminal angles, but finding the coterminal angle also works. Sine and cosine are both what we call sinusoidal functions, and all that means is resembling the sine function. Sine and cosine, their graphs are very similar. You can think of sine as just being cosine shifted to the right pi over 2 units, or cosine being sine shifted to the left pi over 2 units. But both are what we call sinusoidal functions.